Now, so the next concept we want to discuss about is the concept of continuity. So, okay. So the idea is, suppose you have a point A. If you can draw your function across A without lifting your pen, then the function is said to be continuous at that point. Now, of course, this is not a proper definition. This is just an intuitive definition. And this is a definition we want to make it solid, or rather precise, using mathematics. Okay. So let's see an example here. So suppose you're given at A, your function goes like this, but there's a hole like that. So this function is not continuous at A, right? Why? Because you have to lift your pen up and then proceed from here, right? So for function to be continuous, your function value should have been defined at this point, right? So the first thing you need for continuity is that f of A is defined, right? So f is continuous at A if f of A is defined. Now let's look at second case. So second case is this one here. In this case, you see the function is, what do you have? The function is defined at A because this dot here represents that the function is defined at A by that value, whatever that value is. However, the function is still discontinuous, or sorry, let's say the function is still not continuous. Why? Because the idea is you go down like that, and then you have to lift your pen up and then draw it. So for that to happen, for function to be continuous, what should have happened is if you go like that, or if you come like that, you should basically reach to the same point, right? So what should have happened is limit as x goes to A, f of x should have exist for the function to be continuous. Yeah, like here, if you come from this side, you still get to the same value. If you go from this side, you still get to the same value, right? So the limit as x goes to A, f of x should exist. And not only that, third, let's look at the following scenario again. I'll modify the same graph. So I have A, I have function defined like that, but instead of function being defined at A by this point, it is defined by this point. So in this case, again, the function is not continuous because when you have to draw across A, you go like that, but then you have to lift your pen, go up, and then come down again like that. However, this problem would have been fixed if this point was defined, f of A would have been equal to this value, right? So we need limit as x goes to A, f of x. This limit should be equal to f of A. So both of these conditions can be combined in the third one, right? Because when you write it like this, you're already saying f of A is defined, and you're already saying that the limit exists because you're saying that limit is equal to f of A. So this is what the definition of continuity is. A function f is continuous at number A if limit as x goes to A, f of x is equal to f of A. This would mean three things. This would mean that your A belongs to the domain of the function. Second, limit as x goes to A, f of x exists, and limit as x goes to A, f of x is equal to f of A, as we saw earlier. So this is equivalent to these three conditions. Yeah. So let's move ahead. Now, what does it mean by a function being discontinuous at a point? So now, if you want to talk about discontinuity at a point A, First of all, the function should be defined around A. Otherwise, you do not talk about discontinuity at that point. So function should be discontinuous, that should be defined around A. So in this case, for example, the function is defined around A. What does it mean by around A? In a open interval containing A, the function should be defined except at A. And the function should not be continuous at A. Then we say the function is discontinuous at A. Okay. That is the idea behind the discontinuity. All right. So, all right. So let's look at the following problem. So where are the following functions discontinuous? Right. So let's see, what do we get? In this case, let's see. So when A is, so something is happening at 2. So let's investigate first at A equals to 2. So what is this problem asking us? Where is this function discontinuous? Right. So consider case 1, consider A equals to 2. So what is limit as x goes to A or x goes to 2 of f of x? Now as x goes to 2, x is not 2, right? So you can write, what is the definition of function when x is not 2? It is this thing here, right? So this is going to be x squared minus 4 upon x minus 2. This is limit as x goes to 2. Now you can factorize the numerator, is going to be x minus 2 times x plus 2 over x minus 2. Why did I do that? Because it's of 0 over 0 form at 2. Then we cancel these guys and you substitute, you get what? It's equal to 4, right? Because it's 2 plus 2, which is equal to 4. So if you want to write down the step, this is going to be limit as x goes to 2 of x plus 2, which is 2 plus 2, which is 4. But f of 2 is what? But f of 2 is equal to 5. So therefore, what do we get? Since limit as x goes to 2 of f of x is not equal to f of 2, what do we get? In that case, f is not continuous at 2, or f is discontinuous at 2. F is not continuous, but f is defined in the neighborhood, in the open interval containing 2. So f is defined actually for all real numbers, right? So f is, instead of not continuous, I'll write f is discontinuous at 2. Okay. Now let's look at the other points. So consider A is not 2. In that case, what do we have? Limit as x goes to A of f of x is equal to limit as x goes to A of x squared minus 4 divided by x minus 2. Now note that A is not 2, so this is equivalent to a rational function, right? And this, since A is not 2, A belongs to the domain of this function. So therefore, by direct substitution property, you will get this is same as, yeah, this is when A is not 2. And also f of A is, since A is not 2, f of A is given by what rule? F of A is given by this rule. So you get f of A is A squared minus 4 upon A minus 2. So what do we get? So this limit, since limit as x goes to a of f of x is equal to f of a, f is continuous at all a not 2, right? So therefore, what do we get? Only point of discontinuity is, so f is discontinuous. Where is f discontinuous? F is discontinuous at 2, right? Now, how does the graph of this guy looks like? Let's try to attempt to draw the graph of this function so that we have some understanding. So at x equals to 2, the value is 5. So 1, 2, 5. So at 2, the value is 5. Otherwise, if x is not 2, you can cancel the common factors x and you will get x plus 2. So it's like a line x plus 2, and line x plus 2 looks like. When x is 0, you get 2. So it will be more or less like a line like this. Okay. So this is an example of what? This is an example of what is called as removable discontinuity. This discontinuity can be removed by basically by redefining the function to be this value here. Okay. All right. Let's move ahead and do the next problem. G of x equals to 1 upon x minus 2 if x is not 2, and 5 if x equals to 2. Let me just draw the graph of this function. So this is same as graph of 1 over x, which we have already drawn, but shifted to what? Shifted 2 units to right. Okay. So the graph looks like this. So this graph has a vertical asymptote 2, and then when you draw it, let me use another pen. Right? It has a vertical asymptote. It also has a horizontal asymptote, which is your x-axis. So this is a graph of 1 upon x minus 2 if x is not 2. When x is 2, it's given by what? It's given by 5. So when x is 2, that means at this value, at 2, it's given by 1, 2, 3, 4, 5. So at this point, it's defined by this value. Okay. So now let's try to see where is this function discontinuous. Okay. So again, let's consider a equals to 2. Now, what is limit as x goes to 2 of g of x? That is same as limit as x goes to 2 of 1 upon x minus 2. Because x is not 2, therefore we have to use this definition. Okay. So what do we get? This is, now for this we have to look at the left hand limit and the right hand limit. So limit as x goes to 2 plus, because the denominator is going to 0, numerator is not. 1 upon x minus 2. This is going to be infinity. And limit as x goes to 2 minus of 1 minus x minus 2 is negative infinity. Right? So therefore, this limit, what? This limit does not exist, right? Since this happens. So therefore, what? G is not continuous or is discontinuous at 2. Again, because it's defined for all real numbers. Now, what about the case, next case, when a is not 2? Next case, consider a is not 2. In that case, what do we get? In that case, we have limit as x goes to 2 of 1 upon x minus 2. Sorry, x goes to a, right? We are looking at x goes to a. And now that is going to be 1 upon a minus 2. Why is that? Because this is a rational function and a not equal to 2 belongs to the domain of this rational function. So it's equivalent substituting the value when a is not 2. But this is same as f of a, right? Because that's a definition of f when a is not 2, since a is not 2. So therefore, this gives us what? Therefore, f is continuous everywhere else. Everywhere else means everywhere outside too. So such a discontinuity, this kind of discontinuity is called an infinite discontinuity. Okay. Because the function is going to infinity. Right? So this kind of discontinuity cannot be fixed. The previous one was removal discontinuity that could be fixed. What do you mean by fixed? It can be fixed by basically just changing the definition of function at one point. Here, no matter what you define the function value at 2, the discontinuity cannot be fixed. Okay. So let's move ahead and let's look at the next problem. Okay. So h of x is 1 if x belongs to this interval, and it's 2 if x belongs to this interval. Okay, so then the idea is what at what point is this function discontinuous, right? So let's first draw the graph of this function. So how does the graph of this function looks like? So we have from 1 to 2, and then from 2 to 3, right? So 1 to 2, it's defined by constant 1. So from 1 to 2, it is defined by constant 1. So this is how the function is defined as. And there's a hole because by 2 it is defined, at 2 it is defined by different rule. At 2 it is defined by what? Is defined by 2. So here we have, and again at 3 we have a hole. Now let's see. So what is happening around this function? So where is this function discontinuous? So at x equals to 2, notice that the function is defined in an open interval containing 2, right? However, limit as x goes to 2 plus, what is limit as x goes to 2 plus? Limit as x goes to 2 plus is So if you look at limit at x goes to 2 plus h of x, if you approach to 2 from this side, your function has what? The function value is going to 2. So limit as x goes to 2 plus is 2, which is same as h of 2, right? Because h of 2 is 2. But limit as x goes to 2 minus h of x, what is, if you're approaching to 2 from the left side, this side, you have h of x is going constant 1. So you have limit of x goes to 2 minus h of x is 1. So since the left hand limit and right hand limit are not equal, we get what? Limit as x goes to 2, h of x does not exist because the left hand limit and the right hand limit are not equal. Okay. So such a discontinuity is called, a function took a jump here. So this kind of thing is called jump discontinuity. So there are three kinds of discontinuity: removable, as we saw, removable discontinuity, which we saw here. The second is infinite discontinuity, and then the next one is jump discontinuity. Okay. So now note, however, we have limit as x goes to 2 plus of h of x is h of 2. So the function is not continuous at 2, right? Because it's discontinuous at 2, right? So jump discontinuity at 2. However, we can say that at 2, the function is continuous from right. So let's have the concept of continuity from one side. You will see later on why this concept is important, particularly when we are only interested in continuity of a function on a closed interval. Okay, so here we say a function is continuous from a right at number a if limit at x goes to a f of x is equal to f of a. So you can see in this case the function is continuous from where? From right, but not from left. Okay, now what is the continuity from the left? So f is continuous from left at a if limit of x goes to a minus f of x is f of a. Okay. So this leads us to the following definition. A function is said to be continuous on an interval if it is continuous at every point inside the interval. So suppose you have a function like that. You have function from a to b. And suppose you have a function like that. So this function f of x is continuous on, f of x is continuous on AB. Why? Because inside it's continuous at every point here. And at this point, it is continuous at what? So at this point, here it is continuous from where? Continuous from right. And at this point, it is continuous from where? From left. Okay. So this is the idea of continuous on an interval. Okay. Now let's look at the next problem. So find the number c that makes f of x continuous for every x. So now, if x is not 1, then this function is rational. So only problem of discontinuity is at x equals to 1. So only problem is at problem with continuity a possible problem, only problem, or rather say possible problem or obstruction with continuity is at x equals to 1. Yeah. So any possible problem could be at x equals to 1. So let's investigate what is happening at x equals to 1. So let's look at this. So limit as x goes to 1, f of x should be equal to f of 1 for continuity at 1, right? If f is to be continuous at 1, then this limit should be equal to f of 1. So now we have limit as x goes to 1 of x4 minus 1 upon x cubed minus 1 should be equal to f of c if this function is continuous at what point? At x equals to 1. So now let's try to find out the value of c from here if it exists. So this is going to be limit as x goes to 1 of x to the 4 minus 1. So when you put 1 on the top, you get 1 to the power 4, which is 1. 1 minus 1 is 0. So there's a factor of x minus 1 hiding there, which we need to get out. Similarly, in the denominator as well, if you have put 1, you get 1 cubed minus 1 is 0. So that means there's a factor of x minus 1 hiding there. So we need to expand it or factorize it to get the factor of x minus 1. So for that, notice the following. If you take x to the n minus 1, the formula is x minus 1 times x to the n minus 1, x to the n minus 2, dot, x plus 1. Yeah. So to see that this is true, you can multiply it out and check. So let's multiply it out and check. So let's multiply x with every one here. So in that case, what do you get? You get x to the power n x to the power n plus x to the power n times, 1 times n minus 2. So 1 plus n minus 2, which is going to be n minus 1, x to the power n minus 2, so on. This term is going to be what? X squared, and then the last term is going to be x. Now multiply everything with minus 1. So you have minus x to the n minus 1, multiply minus x to the n minus 2. Then this would be minus x. Then the last one would be minus 1. So you see that everything in between will get cancelled. Yeah, this term will get cancelled, right? So this is dot. So all the terms will get cancelled except the first term, and the last term will survive. So you will have x to the n minus 1. So this is an expansion for all of them. So let's finish this problem. So what is the expansion for x to the power 4 minus 1? It's going to be x minus 1 times x cubed plus x squared plus x plus 1 divided by x minus 1 times x squared plus x plus 1. Now you can cancel these factors off. These two can cancel off. And now when you put 1, what do you get? You get 1 plus 1 plus 1 plus 1, so 4. And in the bottom, you will get what? You will get 3. And that should be your C. So therefore, what do we get? Therefore, C equals to 4 by 3 makes F what? Makes F continuous for all x. That is the idea behind it. Okay. Now, so that is how you find out the C. Again, it relies on the definition of your definition of continuity. What does it mean for a function to be continuous? Right. Okay. So let's move ahead and try to do the following problem. Let's do this problem. So now, given f of x equals to, so this is an example of, again, a piecewise function. Now the definition is as follows. So on, you have 0. At 0, the function is defined as 1, right? So the function is defined as 1. On this side, so let's call this as g of x. If you call this as g of x, in this side, the function is defined by g of x. Sorry, on this side, it's, and this b h of x. The function is defined because -1 to 0. So in this side, the function is defined by h of x. And on the other side, until 1, the function is defined by what? G of x. So on both sides of 1, the function is defined differently. Yeah. So now we need to find out values of a and b such that this is continuous on -1 to 1. Yeah. So for that, what we need is limit as, so there's something happening, interesting happening at 0. On both sides of 0, the function is defined differently. So we need, for function to be continuous at 0, we need that limit as x goes to 0 of f of x should be equal to f of 0. Yeah. Why did I choose this? Because this is a connecting link between the first function and the second function, right? What do I mean by that? It's connecting link between h of x and g of x, right? That's how we can connect it and find the values of a and b, because our goal is to find values of a and b, which will make it continuous. Now note that this could also mean that there's, I mean, if you find out that, if you work it out, you could also find that there's no values of a and b which will work. Yeah. So that is also a possibility to keep in mind. Just because the problem is asking you find a and b for which this is continuous doesn't mean that there exists such a value, right? But okay, so let's embark on this. Now, since on both sides of 0, the function is defined differently, we'll have to take a left-hand limit and a right-hand limit. So this limit is 0 is same as saying limit as x goes to 0 plus f of x should be same as limit as x goes to 0 minus f of x. That should be f of 0, and well, that is 1 to us. So now let's compute limit as x goes to 0 plus. So in that case, we'll use the function. So we are approaching to 0 from this side. So we'll use the definition of function to be, so the function will be given by limit as x goes to 0 plus of square root of 1 minus x minus 1 divided by ax. Right. So again, when you put 0, you get 0 or 0 form. So you need to get a factor of x minus 0, which is x out. All right. So there's factor of x already in the denominator. So we need to rationalize it. So let's rationalize it. So this limit is same as this multiplied by 1 minus x plus 1 divided by 1 minus x plus 1. So I'm rationalizing it, rationalizing using conjugate. Yeah. So I should write it down. What I'm doing, I'm rationalizing using conjugate, or by multiplying the conjugate. So then this becomes limit as x goes to 0 plus 1 minus x minus 1, a square minus b square. And denominator, you still need x, so you will not multiply it out. You'll keep that x intact because that will be used to cancel out. So this one and this one can cancel, right? So this is going to be limit as x goes to 0 plus this minus x and minus x can cancel out as well. So let me just write down the next step. So I'll cancel out these guys. What do I get? This is going to be limit as x goes to 0 plus 1 upon a times square root of 1 minus x plus 1. And then what do we get? As x goes to 0 plus, this is going to be a times square root of 1 plus 1, which is 1 by 2a with a minus sign. And that should have been equal to f of 0, which is 1. So from there, you get what? A should be minus 1 over 2, right? You multiply this a on the other side. Now, similarly, what should happen? So for continuity, 0, x goes to 0 minus f of x should also be f of 0, which is 1. So now in this case, the definition of function is what? Limit as x goes to 0 minus, what is your f of x? Your f of x is, as x goes to 0 minus, on this side of 0, the function is given by this definition. So we have b x to the 4 plus bx divided by x squared plus x. Now this is again 0 0 form, so we can take common factors out. So we need to pull out factors of x. So I can pull out x from top. I'm given b, and also I can pull out b as well because b is common. I get x cubed plus 1. In denominator again, I pull out x common. I'm left with x plus 1. So these guys can cancel each other off. And when I put b equals to 0, now I can put x equals to 0. I get b times 1 over 1, which is b 1. Why? Because this is same as f of 0. This is f of 0, which is 1. So therefore, what do we get? Therefore, b equals to 1 and a equals to minus 1 by 2 make f continuous at what? Make f continuous at 0, and hence on all of, what is the interval? The interval was minus 1 to 1. So this is the part, right? So